Lab 4, Spring and Oscillations. Alright, so a little introduction about the lab. Basically in this lab, we're analyzing a spring mass system, which is oscillating and moving in an oscillating motion in order to study the relationship between the kinetic energy, the gravitational potential energy, and the spring potential. The main principle that we're going to be using in this lab is the energy principle, which is delta E equals the work of the surroundings. And we can break this down to three components: the change in kinetic energy, the change in gravitational potential energy, and the change in the spring potential energy. So in this lab, the system is closed and delta E is equal to 0. We will see how this relates to the results later on. Alright, so the next step was to acquire experimental data. So basically, in order to do this, we used the tracker software to get the X and the Y positions as the time went on. And we were given the mass and we were given the calibration length. So first step was to solve for the period. As you can see, we can just use the information from tracker to solve for the period, which we got to be 1.56 seconds. And then we can find the spring constant using that formula. The period equals 2 pi over the square root of m over k. We got 652 for our spring constant. And finally, using our spring constant, we can solve for the initial length of the spring, which we got to be about 0.0957 meters. All right, so now we move on to our code part of the lab. So in this part, we had to write a code in order to compare our experimental data to a data that already existed and see how accurate they were. So basically, we can insert the mass that was given, the spring constant, and the length that we just found. And then we need to solve for equations for L hat and S in order to be able to get these values and input them into our spring potential energy equation. Now, we know that kinetic energy is equal to 1/2 mv squared. So we just input that in. We got mgh for potential energy. In this case, the position will be h. And then we just input the spring potential energy that we learned this week, that equation from the values we just found. And yeah. And then as we continue our code, we can use the components that we calculated on the first part of the code and put them together to get a net force. And as you can see, our net force is just composed of two components, which will be the force of the spring and the force of gravity. So we just do that, and in order to get the velocity and positions, we can just do the velocity and position update equations from the, Newton's second law, which we already know. So now let's look at results. Alright, so now we can look at the results in the summary from the experiment. So as you can see, we have two main graphs here. One is the change in energy over time, and the other is position over time. So first, let's look at the change in energy over time. Now, the orange line represents the total energy, and as you can see, the total energy remains 0. This makes sense because the spring system is a closed system, so there is no external work being done on the system. Now, you can also see that when the change in potential energy is at its highest, the change in kinetic energy is at its lowest, and vice versa. Now, moving on to the position versus time graph, as you can see, it follows the same trend as the code that was already inputted. So our experiment is pretty close. However, as as like the time goes on, they seem to separate, and the experimental graph seems to have a smaller amplitude. This could be due to observational error when clicking in tracker and other forces applying on the system, such as drag and air resistance. So to summarize this, let's answer the what does it mean questions. So first off, is the energy principle satisfied for models? And yes, the answer is yes, the energy principle was satisfied. As I was saying in the last slide, you see the total energy will always be 0 because it's a closed system, so it is satisfied. And then we can make two separate estimates of oscillation periods. First, by estimating the period from the X position, and then comparing the period to the Y position. And so as you can see, I just did them right there from tracker, and they're kind of inverses of each other, right? But the the period of the X is a little longer than the period of the Y, and since they're not the same, we can infer that the motion of oscillation that is being done is not a perfectly good circle, but rather more like an oval shape. And that is my lab. Thank you for listening, and yeah, thank you.